Well, you find it in here. And you know the reason for having the common ion effect, that tells you the ionic strength.
So you use that point.
You have to use the 0.1 because it's a 1-to-1 salt. And we'll work through it. Just give it a shot first. 0.38. Oh my goodness. Where the hell is iodate? See, make sure you've got, you should have been started. You haven't got started yet. Let's see if I can at least get you started, or someone around you got you started, right? So you write the KSP reaction, okay? So everyone's got that so far? And I'm not worried at all about activities or activity coefficients because I don't have any equation that has a concentration in it yet. So I don't care. I'm going to do everything we did before in the past, not changing a thing. So what do? Well, we made our little ice table, right? Because solubility is X in ice. So hopefully you did this, right? I know it's a funky quaternary salt, but that's just how life is. Just gotta, right? But what helps me though is to know those polyatomic ions. I'm comfortable with them. I know that that's iodate and has a -1 charge. Why does that help me? Because that means this whole thing, I don't even care what it is, that has to have a +1 charge. So it's got to be one of those 1-to-1 salts. So I know exactly what the ionic strength is. This is going to be my ionic strength. I'm kind of jumping ahead a little bit, but that's got to be my ionic strength. Okay? And I mean, it's not completely my ionic strength. Probably will be a dinky bit higher because there's some barium ions and there's some iodate anions in there, but their concentration is extremely small because this stuff is insoluble. 10 to the -9. Okay, you're going to end up with 0.1. Okay, so I wrote that. Then, hopefully you did what next? Here's getting too big. Write your KSP. Grab it. Right? My KSP is 1.5 to 10 to the -9. And to keep myself from screwing up, I wrote the activities. Right? Because I'm supposed to be worried about activities. So it's a concentration of products over reactants. No, it's the activities of products over reactants. Right? So I have the activity of barium, the activity of iodate, but it has to be squared. You comfortable so far? Right? Nothing really new. It's everything we've been working on before.
So it has to be the entire activity squared.
Yeah, because remember, activities are replacing the concentrations. So then you can see the issue there. So then I have to square iodate's activity coefficient along with its concentration. You know that's going to be the next step, right?
It's squared because it's a 2 now?
Because you would have wrote, in the past, we would have wrote the concentration of barium times the concentration of iodate squared, right? So we're now, all that we're saying now is, Albert, all concentrations have to be replaced with their respective activity. So instead of writing the concentration of barium, activity of barium. Concentration of iodate, the activity iodate. And it has to be squared because it's 2 iodates. Yes.
Before we would normally drop that 2x.
Let's see. Let's see. You still will drop it, right? But I'm not dropping it yet because I don't want to screw up, right? So because I'll end up forgetting to square some activity coefficient or something if I don't do this. So to this day, I have to do all this. I write all the activities, and then by writing the activity iodate squared, I'm going to remember to square its activity coefficient and its concentration. Okay. So that's my method when working with activities. Just replace all concentrations with their respective activity. Then nothing changes. Everything you've been doing up to this point. Nothing changes, right? So where do the activity of barium, I had to look it up. Right? The activity coefficient of barium. The activity coefficient of iodate, I had to look it up. And just like we did before, where do you get these concentrations? You get them from the table. Here's our concentrations at equilibrium. See, that's what you plug in for the concentration. And nothing new. We square it just like always. Okay. And then we said, oh, scratch our heads. Can we drop the 2x? We're supposed to look where? At the KSP. And we can definitely drop it. Okay. You can definitely drop it. So it's exactly the same. It ends up being pretty much the exact same problem. I just have some fudge factors in there.
You just dropped that 2x. That's it.
Because remember, that's what we always did in the past, Jamie. Remember that? There's nothing plus that x.
Okay.
We would if there was like a x plus 1 or something. But there's nothing that we're adding or subtracting to it. So we'll have something like 1.5 times 10 to the negative 9. It's going to be approximately 0.38 times x times 0.775 squared times 0.1 squared. Then we solve for our x. And they didn't say find the solubility in grams per liter or anything. They're just after the concentration of barium. They just want to know what x is, which is the same as solubility, but they just want to know what x is. They could have asked for the concentration of iodate. Could have just said 0.1, right, if they did. So a final answer. Daisy, did you get a final answer? That's my x. That's how I write x. I don't write multiplication signs. It gets too confusing. It gets too confusing to write multiplication signs. So did you get hopefully 6.6 times 10 to the negative 7 maybe? Ah, great. 7. Somewhere around 6. Depends on your digits you're carrying, I guess. Okay. So your game plan should be handling these problems just like we did in the past, whether it's pH, pOH, solubility problems, Ka, Kb. It doesn't matter what we've done. We can handle them all with activities. Okay? Just do everything you did in the past and then replace the concentration terms with activities. Okay? Are you comfortable with it? Try this next one now. Find the activity coefficient of hydrogen ion in a solution containing 0.01 molar HCl plus 0.04 molar KClO4. Then what is the pH of the solution? Try that one. Okay. Man, I am being so nice today. Anybody get an answer for it? Yeah, oh, my boxing's not working. Anybody get an answer? No? Okay, now when you're working this out, the very first part asks for, here I can go like that. The very first part, okay, I think there might have been a homework question like this one. So, yeah, no, okay. You want to use activity. So you know pH is negative log of the activity of H. So you've got two issues that you got to deal with. One is you got to find the concentration of H. But that's not so bad. That's just going to be what? The 0.01, right? Because it's HCl. So to find a pH, it's a negative log of the activity, which is the activity coefficient times the hydrogen ion concentration. Well, the hydrogen ion concentration is 0.01. That part's not so bad. The issue is, how do you get the activity coefficient? So that's got to be on here, right? So you're hoping and praying that it's one of these up here, so you don't have to interpolate for the ionic strength. You've got ionic strength is that equation where you have to identify all the ions in solution. Here it is, this one. Identify all the ions in solution, and you can use this equation. It'll work every single time. What ion, and then, right, it's concentration times its charge squared divided by 2, right? And you recognize all the ions. You've got hydrogen ions, you've got chloride anions, you've got potassium ions, you've got perchlorate anions. But they're all what ratios? They're all 1 to 1. So you can use that equation. It's not going to hurt you at all. It's just, it takes energy. But the ionic strength from 0.01 molar HCl alone is 0.01. The ionic strength from 0.04 molar KClO4 is 0.04. Has to be the concentration, right? The molarity. So if you have 0.01 from the HCl, 0.04 from the KClO4, your total is 0.05. That's what I was thinking. I'm being too nice. I thought this is an interpolation problem, but it's not. It's 0.05 is right on there. You don't even have to interpolate. Okay? So all All right, it has to be for hydrogen ion because this is all you're interested in, negative log of the activity of hydrogen ion, which is its coefficient times its concentration. Okay. And that's pretty different than the concentration would be. So just by adding this salt, the importance of ionic strength becomes, and using activities is really enhanced. Okay. Getting away from pure water and getting into actual real-life solutions, it really illustrates the importance of activities. But notice how this question could have been a lot uglier, right? If recognizing the concentration of hydrogen ion is not so bad, but what if this guy wouldn't have been a one-to-one salt, right? You had to go through the work, but you know how to do it, how to get the ionic strength from it. Don't forget to add on the ionic strength due to the HCl. That still would have worked, okay? So you can start on the homework. This is a handout, so I assume it's some of the homework. So go ahead and start working on this. Now, if there's any questions on what we've done so far or on getting started on this, just ask. Okay, I'll be glad to help you out. So use activities and calculate the concentrations of the mercury 1 ion in saturated solutions of mercury 1 bromide. Okay. Yep.
So you said if your KSP. Right. And so
No, hang on. Here they're giving you
Yeah, that was my
Hg2
first.
plus 2. This has to be Hg2 plus 2.
So it's not 2Hg.
No.
It's like if
No. Yep. It's a diatomic ion.
So then that one's the same thing, right? So this one would have.
That'd be 2 Br minuses.
Yeah. That was my first question. Okay, so
Yeah.
once you have that, you have your KSP set up. Knowing this tells you that you have these ions, right? That it dissociates completely.
So you're going to have 1-to-1. So your ionic strength, all you're really interested in is knowing what the ionic strength is. So you can look up your coefficients. So you can identify all the ions,
This gives you like the ionic strength
of the whole solution
of the whole solution.
because it's a 1-to-1. If it wasn't a 1-to-1 salt, you'd have to use that equation.
So does that mean that I just looked up the 0.001 for both of these?
Yep.
activity
Yep.
coefficients, and
Yep.
That's the only time that that's factored
Mm-hmm.
in.
Yep. Because it's not a common ion. So
Oh, okay.
it's not going to fit in here. But it does determine ionic strength.
Yeah, that's right.
Yep. Yeah.
Okay, I understood that we're setting it up like we were before.
Yeah.
Where does the
Okay. Without this, first, it's not a common ion problem, right? So this will not be in the ice table. But it's there because imagine doing ice, writing the KSP expression in terms of activities. And activities are always the activity coefficient times the concentration. But you got to get that activity coefficient. The only place is here. This is the only place we get these activity coefficients. And they're there. But you have to know what the ionic strength is. The only purpose for this is to give you the ionic strength. That's the only purpose for it.
All right, that sounds good.
All right? And the other trick is, Eric noticed another trick in this. He recognized the KSP reaction. You got to use this ion. Mercury is breaking up into this ion. It's not 2 mercury ions, no. It's breaking up into Hg2 plus 2, right? The mercury 1. So you'd have the solid goes to its ions, and this has to be one of those ions. So what would be the remaining ions? 2 bromides, right? And that's why it really helps know those dang charges, right? All those halides, they're chloride, bromide, right? Iodide. It really helps to remember all those. But this, it's not expected that you know it, but it was given. Okay? And like Matt noticed that, hey, the only purpose of this is so that you can look up the activity coefficients. Because in this table, the one thing you need to know, well, you need to know 2 things. What the ion is that you're looking up, But then you also need to know the ionic strength. The only purpose of this potassium nitrate solution is to give you the ionic strength, because it's not even a common ion. Its sole purpose is to give you ionic strength. Okay? So see if you can get it to work out. Is anybody lost? Spaced out. Mm-hmm. Oh, you have it. You have it. Right. And remember, bromide has to be squared. Activity of bromide has to be squared. So that means its activity coefficient, and its concentration has to be squared too. Right? Where'd I lose you, Daisy? Well, you know that this guy has to be what? What do you substitute in for this? If it wasn't an activity problem, what would you put in for this? Right? The ice table. What would you put in for it? Mercury 2 plus 2. What's the concentration of mercury plus 2 at equilibrium? Right? That's what you did when we did solubility problems, didn't you? You substitute in that for that. You substitute in 2x for concentration of bromide. So we do that, right? Nothing changes. Make sure you square it. Don't square the x, right? Right? So the important part are these guys. Now you got to get them from the table. So if you're looking at the table, you need to know what the ion is. Well, no big deal. We know what the ion is. But you need to know the ionic strength to get it. So this just allows you to know the ionic strength, or determines the ionic strength. Put it that way. That determines the ionic strength.
So that's not a
It is if it was mercury plus 2 or bromide. But it's not. Okay. So mercury 2 plus 2. Oh, gosh. Where is it? I can't find mercury 2 plus 2. I see mercury plus 2.
2 plus 2 is the very bottom left. Plus 2 charge. The very bottom. I'm looking for B on the nose.
Oh, gosh. Okay, left is left, right is right. Shit. Okay. 0.867. Okay. All right, we'll just write it down here. 5.6 times 10 to the negative 23 has to equal 0.867 x. And bromide. There it is. Thank you. 0.964. And I have to square it. All right.
I think we forgot to square that.
Okay.
I think we were supposed to. Oh, you squared
Okay.
it? Okay, so maybe I did it. Yeah, I probably did it all together.
So it's the only other complication that I think that could be thrown in here is just make it so that this is not in the table, right? You'd have to interpolate to get these activity coefficients. That's about the only complication that could be thrown at you. Otherwise, you've got it. Okay. So have a good break. Be safe.